All right, so today we have got chapter 4 of your NASM textbook. So we are officially done with our Memler's textbook. That's the last time you guys are going to tap into that book, was yesterday's chapter on metabolism. So today, we actually have a very tiny PowerPoint with lots of notes in it, because basically all of it is going to be important. And we're going to look at the NASM approach to metabolism and how to understand sort of how this metabolic information has been applied to the world of exercise. You know, like we know how glycolysis works to produce energy, at least for the most part. We know how like the electron transport chain works and all that. Then we know how generally how long those things take to kick in and start processing energy. So if that's the case, we have sort of chapter 4 here, which is going to describe like, all right, well, if we know that this type of thing results in this type of thing, well, then we can do exercise that makes you do this type of thing. That wasn't as elegant as I thought it would be, but basically, if we know that like you will stay in this energy system for this duration of time, then we will apply exercise in that manner, unless our goal is to, you know, target metabolism in a different way. So it kind of depends on like what it is you're trying to achieve. What are your clients' goals? You know, are they trying to increase like their cellular volume? You know, experience hypertrophy, or are they trying to increase their aerobic metabolism, trying to increase their endurance, you know? And all of that is this conversation around, we call it bioenergetics, right? Which is really just the study of metabolism. You can call it exercise physiology if you want, which is just physiology applied to our world. So the purpose today is to provide basic information on metabolism and bioenergetics, and that'll be useful for us to plan very safe, but also I don't know about more importantly, but also very effective exercise programs for our clients. So we want to be able to, after today's lesson, describe how the body produces energy. So we are going to go through our energy systems again, cellular respiration again, differentiate between aerobic versus anaerobic metabolism. So, you know, talking about like when it's oxygenated versus when it's not, which energy pathways are predominating which intensities. And those intensities actually are not, the intensities actually aren't as important for the energy systems, except from the perspective of like, you know, if it's a high intensity, you should be, you know, working too close to failure by, you know, X number of seconds, or we could say X number of reps, which is what we actually do. Understand how carbohydrates, proteins, and fats are used for fuel during different intensities and different durations of exercise. Differentiate between steady state and exhaustive exercise, which means, you know, high intensity interval stuff. Talk about the differences between intermittent exercise, and then understand like the basic training adaptations that come along with all that. So today, one of our key terms that you will definitely, I don't know if you'll actually have it on your test, but it definitely can be on your test, is this definition right here. So bioenergetics, right? So bioenergetics is going to be the study of how energy is transformed through various biochemical reactions, right? So it's basically describing how the body takes in energy and how it transforms that energy into work, you know, for your new body tissues and all that stuff. So looking at that, that is going to be made up of, when we're talking about this, we're talking about bioenergetics. We're going to be talking about metabolism and exercise metabolism, which are two slightly different definitions, right? So metabolism, any and all chemical reactions taking place in the body, right? Exercise metabolism is any and all chemical reactions that take place inside the body during exercise, which is a very unique situation. You know, our bodies are not by default always exercising, you know, as much as like I'm always kind of harping on us about how active we are meant to be and stuff. You know, your body does go through various different intensities, and exercise is a fairly rare one, you know. And so how does our body interact with its metabolism during exercise is our exercise metabolism. So in order to have a pretty good understanding of that, we have to have a pretty good understanding of our nutrient substrates, right? So your nutrients that you've got are your proteins, fats, and carbs, and the substrates of those are going to be amino acids, fatty acids, and monosaccharides, right? So we're going to take all those nutrients in, convert them into substrates so that they can be used for either fuel or maybe bodily repair, different physiologic functions here. So the first one we're going to talk about is, arguably the most important when it comes to energy production, just like having enough energy to do work. But that's going to be carbohydrates. So carbohydrates, right, are the main source of fuel inside of our body, right? They're our body's preferred source of fuel. We love using carbohydrates for energy. And so when we do that, because we love it so much, we need to have like a really good storage form of this at all times. Like you can always just take in carbohydrates and simply break them down. And by breaking them down, you immediately release like a lot of energy, in the form of like ATP. But you also have some interesting byproducts, right? You've got this pyruvic acid, which is going to build up, and because it's building up, and because all of this is happening in the fluid portion of our cells, that buildup causes like the buildup of lactic acid, right? So that's, carbohydrates are a really good source of immediate energy because they can be broken down like that. I mean, like super, 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 super fast. But it only provides about 2 molecules of ATP for every 1 molecule of glucose, and it produces like a lot of those pyruvates. So you may be able to produce a lot of energy very, 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 very rapidly, but you are also going to get exhausted fairly rapidly as well. But you're going to be producing, energy like really super small amounts, like very, 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 very quickly. And that's great if you're doing a sprint or lifting really, 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 really heavy, and you're keeping your exercise intensity so high that your duration is, anywhere under a minute, basically. That's a great way to remain using carbohydrates. Now, they're going to continue working in the background because, again, like they're supplying all this byproduct in the form of pyruvates, which ferment into lactic acid. And that lactic acid is a great fuel source for our other energy systems. So because our body loves carbohydrates so much, I mean, like that just sounds like a really efficient use of things, right? If I describe that, you're like, yeah, that sounds pretty efficient, right? Like we get something out of the initial, fuel source, and it leaves us with a byproduct. But then that byproduct gets used as a fuel source in the next energy system, giving us more fuel. And then that byproduct gets used in the next energy system, giving us even more fuel. So that's awesome, that's a really freaking efficient. If we can figure out how to do that, like apply that to, friggin' fuel around our planet, like we'd be doing great. If we could have figured out how to like take the exhaust from our car, like all that carbon monoxide and stuff, if we could have taken all that exhaust and used it as fuel for other cars, like we had half gasoline running cars and half carbon dioxide running cars, like we'd be in great shape. There'd be no greenhouse gases floating around the earth. But it doesn't work that way. Just to be very clear. Anyway, that's why we love carbohydrates so much, and we love to store carbohydrates in our body so that we don't run out of our preferred fuel source. So how do we store those carbohydrates in our body? Well, we store it in the form of this material called glycogen. Glycogen is basically these big, complex, this big complex chain of carbohydrates all linked together. And we store it mostly in like our liver, but also throughout all of the muscles inside of your body. And so by having all of those carbohydrates stored, about 1% of your body weight stored in carbohydrate form, we're able to break those down anytime we run out of energy. So if you're, out there on the road running, and it's been a couple hours, luckily, your body has plenty of carbohydrates to kind of tap into. The next substrate that we've got is obviously fat. Fat is another really great way for us to produce energy. So fat provides the body with energy as well. In fact, fat actually has more energy in it than carbohydrates do, at least per gram, which is kind of funny. You think about like how much ATP would be locked in a molecule of glucose versus how much ATP is locked in a molecule of fat. There's actually more energy in fat. That's why fat has 9 calories per gram, and carbohydrates only have 4 calories per gram. And protein has 4 calories per gram as well, just while I'm talking about it. So you think about like fat, It has a ton of energy in it, right? So that's really good if we have like, low sustained energy, because here's the thing, like fat may have a lot of energy in it, but it takes a little bit longer to access that energy. Getting to that energy is a little bit more of a pain in the rear. So because that process just takes a little bit longer, fat is really, really good for low intensity, long duration activity. So like right now, you guys are probably sitting down, I'm assuming. I know I am. And so I'm not exactly at like a high intensity right now. Like we're pretty much chillaxing. We're not really doing all that much work. So because we're not doing that much work, our body is mostly sustaining on its ability to burn fat as an energy source. So we're mostly in like the fat burning zone right now. If we were to lay down, we would actually be even more in the fat burning zone. And then if we were to fall asleep, we would be 100% in the fat burning zone. So when your intensity is at its absolute lowest, that is when you are burning most of your energy. Most of the energy that's being burned to keep your body alive is coming from fat, because this is a very long duration activity. This is something, you're going to sleep for hopefully 8 hours, So because you're sleeping for like this long duration, you're in this like low intensity for such a long duration, fat is our primary fuel source. Now, when we're doing high intensity activity, like I said, like glycolysis is something that produces energy very, very rapidly. So if you all of a sudden switch into super intense, rapid, you're standing there doing nothing, and then all of a sudden you're like, I'm being chased by a bear, and you start sprinting, right? That sprinting action is very, very, very high intensity. So it's going to primarily rely on carbohydrates as a fuel source. So you're always in like a blend between like a mixture of carbohydrates versus fat in terms of like what you are primarily burning. So fat may yield the highest ATP per gram because it's got the most calories per gram, but that doesn't mean it's your body's favorite fuel source. Your body prefers to use carbohydrates at high intensities. But we're not at high intensities very often. So, that's why it's so important to make sure that like, yeah, you're giving yourself carbohydrates before like an intense workout, but do you need carbohydrates to sustain on when you're doing like relatively low intensity work? Maybe not. This is one of the reasons why, again, like ketogenic diets have been so popular in the last few years. A lot of people have come to realize that like they don't do that much high intensity stuff that often. We have a lot of desk jobs. We have a lot of sitting around. So the idea there is that like, well, why would we give ourselves the high intensity fuel if we're not going to use it? And I actually like that approach. I think that's a very logical, sensible thing to do. However, one of the issues with this is that if you are only ever relying on that low intensity fuel source and that low intensity work, when you go to do high intensity work, which by the way burns more calories than low intensity work, that should go without saying, you aren't going to be able to work very hard because you don't have the right fuel source. So again, like I like a balanced diet personally, but I can definitely see the logic behind like a ketogenic diet. Our third fuel source is going to be protein, but our body prefers not to use protein, tries not to, right? But protein can be used for energy production, but we really don't want it to for a couple of different reasons. Your body will try to not use protein because it's trying to use protein to repair your body's tissues. Any damage, any cellular damage that was created, your body is going to try to use protein to repair that, rather than using it for like energy production. But we can do this process called gluconeogenesis, which is where your body can take an amino acid. And if we just pull up a regular amino acid here, amino acid versus a carbohydrate, glucose. Whoa, glucose. I forgot how to type for a second. Let's just look at an amino acid here. There's amino acid, right? Hydrogen, nitrogen, carbon, and oxygen. And then this R group here is just more nitrogen. So actually, here's a kind of a better picture, right? Hydrogen, oxygen, carbon. Those are the big three. And then nitrogen is what gives it its unique shape. So the R here would be a unique shape of nitrogen, and then a little bit of nitrogen here. If we look at a molecule of glucose, glucose is just hydrogen, oxygen, and not seeing any carbon here. There's a ton of carbon. I don't know why. There you go. Carbon, hydrogen, and oxygen, right? So lots of that. So if you were to just strip the nitrogen out of here and just get rid of it and just strip that away, you would be left with all the ingredients for a carbohydrate. And so, boom, you will have converted it into glucose. That is the process of gluconeogenesis. So the formation of glucose from non-carbohydrate sources such as amino acids. Now, this is exactly what you hear about when you hear about people. So I'm sure you guys have heard this where they say, hey, you got to make sure you eat after your workout, because if you don't, your body's going to, and usually people say, cannibalize your muscle, which is actually not like a horrible description. Like I get, because cannibal means to like eat a person, right? So it's like, yeah, your body is eating itself. I guess we could say cannibalize, but the correct term would have been catabolize. Your body is going to catabolize itself. Remember, catabolic reactions are the ones where we're taking something complex and breaking it down. So if you don't get any fuel after your workout, it's theoretically possible that your body will tap into your muscle for energy, right? And you just created a bunch of cellular damage. You just created a bunch of damage while you were working out. So now you're tapping into that, creating more damage, right? That's where we hear about like why it's so important to eat after your workout. Now, I will say this. It's not always super, super, super important to eat after your workout. You may be fine not eating after your workout. You may be absolutely fine. If you had plenty of protein in your diet and your amino acid pool is full, maybe you got a really high protein meal earlier in the day, and so there's a lot of just amino acids running around in your body right now, that could be fine. If the levels are totally normal, you're good to go. Same thing is true. If you get a meal like a little bit after. This is one of the reasons why, and I used to have this problem. I tend to I swear I have like I joke about this all the time. And it is mostly a joke, but I don't know. I swear I have like a weird version of OCD. Like OCD people are like very, usually like very clean and very orderly. That is not the case for yours truly. But I am sometimes like obsessed with doing things as efficiently as possible. So I was just talking about this the other day. Like I have like a paralyzing, I guess call it a paralyzing fear of like leaving the house twice in one day. Like that's not true in terms of like the fear, but like if I know I'm gonna go out to go get groceries and I also know that I need breakfast, but it's like, or like I know that I need like lunch or something. It's like, I'm hungry. I need to go get lunch. But if I leave the house, I also need to go grocery shopping. And I don't feel like going grocery shopping right now. So I'm just going to sit here miserable and hungry. Like rather than like, go do one of that. Because I won't leave the house twice. If I won't go get food, come back and then go grocery shopping later. And it's this weird like efficiency thing, right? So back in the day, I used to have this problem. And let me hear if you guys have this problem as well, because I know a lot of trainers struggle with this, where I'd be like, I know I didn't get a very good pre-workout meal. I should just skip my workout or like push it to later today, so that I can get fueled up and then I can do a much better job of workout. Or I know I'm not going to get a very good post-workout meal. I'm like struggling on time. My diet's really bad this week. What's the point of even working out if my diet's so bad? Because that's all that's going to do is, I'm not going to get anything out of it, right? That's a very flawed paradigm, by the way. But if you've ever had thoughts like that, I know that I do as well. I've had clients who, well, you're going to have clients the same thing. They're going to have these thoughts. And the idea is it's like, yeah, well, like what happens if I lose muscle because like I know I didn't get enough protein after my workout? Honestly, guys, if you have enough protein in your diet, you're probably going to be fine. You don't need to use protein shakes after your workout. You can absolutely get away with whole food. It's not like cave people had protein shakes. Can you imagine? Just like Og and Gronk sitting there like shaking up a protein drink, chasing down a woolly mammoth. So like, there's, as long as you're getting like a normal, like, healthy meal with sufficient protein levels, you're probably going to be fine. But if you don't, let's say you don't get enough carbohydrates in your diet, and your body needs to start producing energy, your body may start converting proteins into carbohydrates to be used for high intensity energy. If you have sufficient protein levels in your blood, you're probably fine. But like if you're really going overboard in the protein, you're probably okay. But if you're not, then your body's going to try to find the nearest source of protein, which is going to be your body. So it is important to make sure you're getting enough food in your diet. And it is important to make sure that you're working out at intensities that make sense, based around your diet as well. So any questions on that, guys? Any comments? Do you guys have those problems as well? I know that I used to struggle with that for years. I'd be like, my diet's not perfect, then why even do it? If it's not perfect, why do it? What is it? Somebody said, don't let perfect be the enemy of good. Good, consistent work is better than perfect, inconsistent work. All right. So speaking of work, right, let's go ahead and talk about how we produce all this energy. So when are we talking about energy? When we are talking about it, we are talking about this molecule called ATP, or adenosine triphosphate, right? If we look at that, that's going to be a molecule. It's going to be an adenine molecule, which is attached to this little sugar called ribose. And then it's got these three little phosphates attached to it. So if we do adenosine triphosphate, it looks like this. I love this version of the picture. You can see here's your adenine, which is, a protein. And then we see here's ribose, which is a sugar. Actually, this is actually really similarly shaped to glucose, just slightly different. But we would call this adenosine triphosphate, right? Because now there's three little phosphates attached to it. So here's your adenosine, here's your triphosphates, right? So adenosine triphosphate. So that's our ATP molecule. Now, there is a ton of energy. Here's a slightly different looking version of it. There's a ton of energy trapped right here between this final bond. So if your body breaks that bond, all of that energy is released, and it allows our cells to do all of their work. It allows our cells to do stuff, right? So ATP is a molecule of adenosine with three phosphates attached to it. There's a lot of energy trapped between the bonds of those phosphates, particularly the second and the third, although there is energy trapped between this bond and this bond as well. But most of the energy is in the second and third. And so when the bonds that hold that ATP are broken, a whole bunch of energy is released. And that energy allows our cells to do stuff. It allows them to have enough energy to kind of move around, maybe create like a muscular contraction, generate tissues. Maybe it's like, anabolic reactions where your body's building something up, that takes ATP. Maybe it's a catabolic reaction where it's breaking something down. That generally creates ATP, but some of those catabolic reactions take energy as well. So, it's kind of funny. It's like you got to spend money to make money, that's how ATP works. You're burning up glucose to maybe get better at burning up glucose. And that's why this is like a consistent process, Now, when you're done with that ATP, you are left with that phosphate kind of floating around there, and you've got two phosphates attached to that adenosine now, which means you would no longer have ATP. Now you have ADP, or adenosine diphosphate, for two phosphates, right? And ADP also has energy, and so you could break that down into what we call AMP, which is adenosine monophosphate. But generally, your body's just going to reconstitute it back into ATP. And how it's going to do that is what we're going to start by talking about here when we look at our energy systems. So, the first energy system that we're looking at, if we look at like our energy systems, let's see if this works. Let's see if I can find a picture of exactly what I'm looking for. Yes. This will work for now. Okay. So here is, not what I want. Oh God, please don't open image tab. There we go. That's a great background, please. Okay, so here is sort of what it looks like in terms of the different energy systems that we've got, right? So you've got your ATP Pc system, which is known as your phosphagen system. You have got your glycolysis, which we call the lactic acid system because it's generating lactic acid. And we've got your aerobic system, which is going to consist of a couple different subsystems there, right? The aerobic system is going to be aerobic glycolysis, which is glycolysis that takes place on the inside of the mitochondria. We don't talk about that one too often, but it's the stopgap that takes place while the energy systems are switching. We've got the Krebs cycle, or the citric acid cycle, whatever you want to call it. And then we have got the electron transport chain at the end. So those three, aerobic glycolysis, aerobic, not anaerobic, Krebs cycle and electron transport chain are all aerobic energy systems. So you can actually see if we look at like our duration here, right? You know, some of it is going to come from your stored ATP from like the last time you generated it, but that's not going to last long. So we can kind of forget about that one. But then we can see like, here's your ATP Pc system. So your ATP Pc system like ramps up, and it is the primary fuel source from anywhere from about like, you know, 0 to like, we can see about 10 seconds here. But even 10 seconds, guys, if you can get your ATP Pc system to last 10 seconds, you're doing a good job. You're doing great there. Honestly, it probably runs out a little bit before that for most people. So then, boom, this all your energy production is mostly not coming from that anymore. So then in the background, glycolysis starts to kick in, right? That's the lactic acid system. So glycolysis starts to kick in, and then it becomes the premier energy system for quite a while. But then you can only keep that up for a little while, so it starts to kind of die off. And then underneath all of that is your aerobic energy system, which is sort of amping up and like taking over and doing most of the work. Now, this pink line up here is what we see in relation to, we call it overall, when we were saying overall performance. So this overall performance line, you can think of this as if you were lifting at like a percentage of your 1 rep max, right? So if you think about like lifting at like a certain percentage of your 1 RM, right? If you're at 100% of your 1 RM, guess what? You can only lift that maybe 1 or 2 reps, which will take you about 2 seconds. So you're relying primarily on stored ATP. If you're doing maybe up to 5 reps, you're relying primarily on the phosphagen system, which is still a very, very high intensity here, right? But then let's say you start relying primarily on glycolysis. Let's say you're lifting for, you know, 6 to 12 repetitions, right? Well, around 6 repetitions, you're probably somewhere right in here. And around 12 repetitions, you're somewhere probably right over here, which means glycolysis is your primary energy producer, which is why we see like 6 to 12 reps, you're not going to be lifting as heavy. You know, you're just not. You're going to be lifting still fairly heavy, right? This is like right in the middle of everything. It's very moderate. This is where bodybuilders live, right? They are the jack of all trades, master of none, right? They're not the masters of the heavy lifting, even though you associate like heavy lifting with bodybuilding. Bodybuilders don't lift heavy. They lift moderately heavy. But you think about like a soccer player, like an aerobic athlete, right? They don't lift very heavy, but they can go all freaking day, you know? And they have like incredible amounts of endurance. So maybe a soccer player won't have as high of an 1 RM as like a bodybuilder, and certainly not as much as a power lifter, but their ability to go for like long durations is unparalleled. You know, like they're going to be able to go forever. And so that's where the aerobic system is really providing most of our energy here, right? And you can see this line sort of levels out, this is what we talk about when we talk about like steady state cardio, right? This line really does kind of level out to where it's like, yeah, I could essentially keep this up almost forever, you know? Or you look at like some of those calisthenic athletes, those body weight athletes who are doing crazy high amounts of reps. You know, they've done this like aerobic stuff here, right? So let's look at this from a slightly different perspective. Let's say it's like sprinting, right? So if you sprint for like 2 seconds, you know, there's your ATP stores, but it's not really applicable here. So let's say you sprint for up to 10 seconds, right? Then you're primarily relying on your lactic acid, your ATP Pc system, right? So this would be like if you're doing a 40-yard dash, you know, trying out for the NFL or something, you know, that's, you know, 40-yard sprint or even a 100-yard sprint, right? Those things are going to rely primarily on the ATP Pc system. Then let's say you continue running. So rather than running just, you know, a simple 100 meters, you continue running for maybe 400 meters or maybe 800 meters, right? So, oh boy, I got into a group text apparently. We are going to mute that. So if we look at like a 400 meter, let's see, what's the world record? World record 400 meter dash. It's probably like 48 seconds or something. 43 seconds. Good God. So 43 seconds, right? If you're able to sprint for 43 seconds, right, then that means that you are primarily somewhere in glycolysis. So you are primarily relying on this little green line here, which means somebody running a 400 meter dash is not going to travel as quickly as someone running a 100 meter dash, but they're still going to be traveling pretty freaking fast, right? Again, jack of all trades. Now let's look at what the world record is for the 5K. Which is 12 minutes and 51 seconds. So that is 3.1 miles in just under 13 minutes. Let's see here, 0.51 divided by 60. So that's not right. 60 divided by 0.51. Nope, that's not right either. Okay, maybe it was right. Oh, that's what it is. 60 divided by 51. There it is. Oh my God, what am I doing wrong here? There we go, 0.85. Man, my math skills are struggling. So that means that they ran this in 12.85 minutes. So 12.85 divided by 3.1. They were running a 4 minute and 14 second mile for 3 miles. Pretty impressive stuff. So that is very much, 4 minutes, they are very much relying on that aerobic system, right? So, that is super fast. I mean, don't get me wrong, like 4 minutes a mile is crazy fast, but it's not crazy fast compared to like a 400 meter dasher. And it's certainly not crazy fast compared to a 100 meter dasher. And then it's really not fast compared to like a 40-yard dasher. So that's what we're looking at, like intensities here. And this is why we have different rep ranges. If you're trying to target the ATP Pc system, right? Let's see if I can find a picture of this that's already modified. Reps. Yeah, I was kind of hoping to put these two charts together. Here's the table. This table works pretty well. But I was hoping to find like a version of this with durations like listed on it. But if you think about it, right, in terms of like your energy system, if we see it less than 15 seconds, you're in the ATP Pc system. That's probably 1 to 5 repetitions. If you're relying on anaerobic glycolysis, that's probably anywhere from 10 to 30 seconds. That is probably going to be like 6 to 12 repetitions. And then if you're relying on anaerobic glycolysis, aerobic oxidative glycolysis, sorry, right in here. That's going to probably be your 12 to 20 reps. And then if you want to be pure oxidative, that is basically where you are going for a jog, which we don't really count in reps. I mean, think about like, imagine if you had to like count reps for jumping rope. You're doing 5,000 of those freaking things, and that means that which is why jumping rope is primarily like a cardio oxidative thing. So let's see these energy systems at play here in our notes, right? So the ATP Pc system provides energy for short duration, high intensity work. It replenishes ATP very, very, very rapidly. And I love that it's replenishes ATP, because remember earlier we talked about how we've got our ATP and we break off that phosphate, we're left with ADP. So this ATP Pc system, that stands for the adenosine triphosphate phosphocreatine system. And so we see ATP Pc system, creatine phosphate donation. If we see what this looks like, there we go. So ATP gets broken down into ADP and a phosphate, and you're left with energy. And what will happen is creatine which has a phosphate on it, will actually donate its phosphate and donate its energy to reattach the phosphate from that ATP molecule. So if you think about, like, if you've got this little molecule here, you break it off and a whole bunch of energy gets released, creatine has this enzyme in it that allows you to reattach that phosphate, which restores the energy so you can break it off again. So you just like crack, 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 and just release a whole bunch of energy really, really rapidly until you run out of creatine. And when you run out of creatine, then suddenly you need another energy system because you're not reattaching that phosphate anymore. This is why taking creatine supplements are so popular, and why it's one of the few supplements you will hear me say has been proven to work as long as you're a responder. Some people, they don't respond very well to that reaction. Their body just is like, nope, not my favorite energy system. So the ATP Pc system is using phosphocreatines, or creatine, to reattach that phosphate back on. And you can do that for about 6 to 10 seconds. That was close. So then you're going to move into glycolysis. Glycolysis is going to provide energy through the breakdown of glucose to create ATP, and this is your moderate duration in work, right? So what we're talking about here is we're talking about anaerobic glycolysis, right? Because until now, all of this has been happening outside of the mitochondria of your cells. But it is taking, I mean, obviously it's taking place inside your cells. It's just not happening in the mitochondria. So all of our cells are fluid-based, right? So there's not any oxygen inside these cells. So this is a very anaerobic situation here, right? So the energy production are taking place in non-oxygen and aerobic environments, right? So anaerobic glycolysis is providing ATP for about 30 to 50 seconds, but then there is just a little bit of glycolysis that's going to take place aerobically, and we're going to see that in just a second. So glycolysis is great because it produces massive amounts of ATP, but it also produces massive amounts of those pyruvates, which are left sitting around afterwards. And the pyruvates, which is actually, we call it pyruvic acid, it will ferment in this no oxygen environment to become lactic acid. And this is why 6 to 12 reps burns so much. Like, don't get me wrong, like 15 to 20 reps or even going up to 30 and stuff like that burns too, but it's very, very different. It's like, you guys know what I'm talking about, right? When you're doing like really ultra high rep stuff, you're like, yeah, this burns, but like it burns in such a way that I can essentially keep doing it for a very, very, very long time. Kind of like when you're walking uphill, you get like a consistent burn, but it's like not enough to like make you stop. Versus when you're lifting really heavy. Like right now, I'm doing a little bit of an endurance routine. I did a bunch of heavy lifting at the beginning of this year. So now I'm trying to do some metabolic training, which means I am doing anywhere from 15 to 20 repetitions, and I'm only taking 30-second rests. And it's brutal. And so like, you know, it just burns like crazy. I get to like my, 15th or 16th rep, and I'm like almost to failure because my muscles are burning like crazy. I sat down, I only rest a little bit. I'm taking like maybe 30 seconds, and then I'm right back into that burn, which is great because that is very good for creating like a lot of metabolic stress. Not so good for building muscle. That's not really what it's used for, but it's a great way to build up metabolic stress in such a way that like hopefully when I do muscle building stuff later, I'll get more out of it, right? So I'm basically producing massive, massive, massive amounts of lactic acid because I'm staying in that glycolysis. That's taking about 30 to 50 seconds, I'm only, by the way, I'm not doing, this is a very not NASM approach to things, by the way. I'm doing stabilization movements, but I'm not doing them at this slow stabilization tempo, although I totally could. I kind of don't like doing that personally. So I'm doing like a 2-0-2 tempo. So that's 4 seconds per rep, 4 times 20 reps. That's about 80 seconds, right? Which is just outside of glycolysis, but I'll be honest, guys, I don't make it to 80 reps very often. So really I'm doing about 4 times 15, which is giving me about 60 seconds. Now for me, that works really, really well. And I'm right in where glycolysis is sort of going through anaerobic to aerobic. I'm sort of staying right in the middle there, which is exactly sort of what I'm trying to target here. because I'm trying to have a lot of metabolic stress. So we start to see like why these energy systems are so important. You know, the last couple months I've been primarily relying on this, but now I'm starting to work a little bit more on this. And then, you know, maybe I'll go all the way down here, but that's different energy systems depending on like what your goals are. So glycolysis is the medium intensity stuff. This is anywhere from 6 to 12 reps is what we usually consider it for regular anaerobic glycolysis, or maybe you're going, you know, anywhere up to 20 reps, which would be like aerobic glycolysis. So aerobic metabolism, your oxidative metabolism, this is the very complex one. This is where there's a lot of moving parts here. So your oxidative metabolism is like it's the most complex. It's using aerobic glycolysis, which is actually happening where there is some oxygen available, and it's happening inside of the mitochondria. This is sort of acting as like the transfer between like, all right, we're anaerobic and we're aerobic, right? Let's pass it off over to the Krebs cycle. So aerobic glycolysis is a little bit different, but it's sort of acting as the stay over here. Then we've also got the Krebs cycle, right? This is your citric acid cycle, right? And so the citric acid cycle is going to produce ATP using the byproducts of all this stuff. Remember, we've been producing massive amounts of lactic acid in these two energy systems right here. So because of that, we have got such a large buildup of that lactic acid, we can start burning up that lactic acid as a fuel source, which is great, right? So now the Krebs cycle is going to use the byproducts of glycolysis to produce a whole bunch of ATP, while also generating these really high energy molecules called NAD and FAD. Okay, and those are going to be byproducts, which will go through the next part of the aerobic system, which is the electron transport chain, where it takes the NAD and FAD's protons and it squeezes them together to spit out crazy large amounts of ATP. And then any of the leftover carbon is going to get slapped onto an oxygen molecule and become carbon dioxide, or it's going to get slapped onto a little bit of hydrogen and become H2O. So you'll be left with, I'm sorry, any of the leftover hydrogen will get slapped. Your carbon's going to become H2O. Any of the leftover carbon is going to get slapped onto oxygen. Any of the leftover hydrogen is going to also get slapped onto oxygen. And you're going to be left with a little bit of carbon dioxide and a little bit of water as byproducts. So, but that spits out crazy high amounts of ATP. I mean, you were getting, for every one sugar molecule, you were getting 2 molecules of ATP in glycolysis. You were getting 2 more molecules of ATP in the Krebs cycle, and you're getting 32 molecules of ATP in the electron transport chain. So you're getting massive, massive amounts there. But obviously, these two systems, I mean, this system relies on the byproducts of this system, so that takes a while to get going. And this system relies on the byproducts of this system, so that takes a while to get going, right? So because of that, this is our long duration stuff. And by that point, your intensity is dipping. So again, if you're doing above 20 reps, like if you're jogging, you're very much in your aerobic energy system. Now, we've been talking a lot about glucose here this whole time. Well, fat can also be metabolized to produce energy. But obviously, it's not going to go through the process of glycolysis, because that's, you know, it literally means glyco, coming from the word glycogen, lysis to mean breakdown. So we're breaking down glycogen to provide energy, right? This is fat. This is a totally different type of molecule, right? So we're not producing ATP through glycolysis with fat. Instead, we are kind of going straight to this aerobic metabolism here. So fat can be metabolized aerobically through this process called beta oxidation or beta oxidation. And beta oxidation is where we are basically going to oxidize a fat molecule, and we are going to be left with this ingredient called acetyl-CoA or acetyl coenzyme A. And that acetyl-CoA is then going to go through that Krebs cycle. Once it goes through that Krebs cycle, we got a bunch of ATP. So it's able to go through the rest of this totally normally at that point. Because again, fats and carbohydrates are actually the same sort of ingredients, right? They're just in a different shape. And that is also why, like, typically we associate, you know, long duration cardio with fat burning. But here's the thing. We're going to talk about this here in just a second. But typically we associate like long jogging, low intensity work with fat burning, right? And here, it's true. It is burning a higher percentage of calories from fat than any of your other types, right? So like you are primarily, when you are doing low intensity, long duration work, you are primarily relying on fat as a fuel source. That is a true sentence. But the number of calories that you're burning is much lower than if you were doing high intensity work. Oh, for a second I thought I heard thunder. I was like, no way. It's a plane that's way too close to the ground. So when we think about like that low intensity, long duration work, burning fat, it's a higher percentage of fat, not a higher number of calories. If you are burning 50% of 200 calories versus like 40% of 300 calories, the number of fat calories is lower overall. 200 times 0.5 would be 100, right? Versus, I might not have amped this up enough actually. 300 times 0.4, yeah, it's still higher. Okay, let's say 400 calories. So 40% of 400 calories. Oh, I'm going in the wrong direction. I'm so dumb. 50% of 200 would be 100 fat calories, right? Versus like maybe a lower percentage. So let's say 30% of like, 400 calories. So 400 times 0.3. 500 times 0.3. What am I doing wrong here? Why am I so bad at math? I'm so exceptionally bad at math. Numbers are hard. 400 times 0.2. Yeah, 80 fat calories. Good God. Oh, no, I was getting the results I wanted. My brain was backwards. Oh my God. That the numbers were supposed to be higher. Sorry. All right, in this scenario on the left, we are burning 50% of our calories from fat, and we are only burning 200 calories. So that's 100 fat calories. Over here, we are burning 500 calories. And yeah, we're not burning 50% fat. Instead, we're burning 40% fat. So times 0.4. Over here, we're burning 200 fat calories, even though the percentage was lower. So the fat burn was actually higher because the calorie burn was higher. Kill me. So that is energy. That is basically fat burning and stuff. We'll talk more about it here in just a second. So we're looking at work versus duration here, just kind of going back to our different energy systems, right? So the amount of energy from stored ATP, like in a phosphocreatine situation, is really limited, right? You can only keep it up for a little while, which is why it only lasts like 5 to 10 seconds, right? So the big rules to remember here, guys, as intensity goes up, duration will go down. As intensity goes down, duration can go up, right? Which is why like walking, you can do it for hours and hours and hours because like that's not a very high intensity. But sprinting, you can only keep up for a few seconds. So the ATP Pc system is very rapid, but can only do it for a limited time, and it's relying on that phosphocreatine, right? The amount from that is pretty low. Glycolysis provides energy for like moderate intensity, moderate work. And so that can, we can rely on that for a pretty long duration, but not that long. Like, the amount of energy from carbohydrates has a much greater capacity, but still very limited. Only 1% of your body weight is carbohydrates. So it's not that much, right? So the amount of glucose that you've got for ATP production from glycolysis is still relatively limited. But then when it comes to fat, the amount of fuel from fat is essentially unlimited. You could do this forever. This is where you hear about, what's that guy's name? Charlie, was it you who was asking me about it? What's the guy who ran a marathon every day?
David Goggins?
Yeah, oh, David Goggins did do it. Yeah, David Goggins is another one. That's not who I was thinking of. But yeah, let's look at David Goggins.
He's a savage.
Dude, yeah, he's crazy. How many marathons did he run? He did such a crazy amount. Yeah, he did the Badwater Ultra Marathon. Badwater is crazy, by the way. This marathon, the Badwater, it goes through Death Valley, and it is one of the most dangerous races that you can do. People, when they're doing Badwater, so it actually gets so hot there that you will see people, they will be very careful. And take a look right here. What do you guys notice about where these people are running? See if you can put this together. Think about how hot it is.
I mean, it is a desert, right?
It is the desert, but see how it is a paved road. Do you notice how they are running on the white line?
Yeah.
That keeps their shoes from melting. That's why they do that. You'll see everyone will stay on this white line while they're running this marathon, because this is reflecting some of the heat, so it's not as hot, so their shoes don't freaking melt.
Yeah, that's crazy.
Yeah. If you ever want to hear a really great story about Badwater, they're on that line. People using squirt guns to keep them cool the whole time. That's the thing. You got to do this with like a team of people, by the way. But notice every picture we see, right? They're all on that white line. Read Born to Run. It's a great book all about like ultra marathoning. It's my favorite book I've ever read. It's literally my favorite book. I love it so much. Anyway, so yeah, he ran friggin', let's see here.
135 miles.
Yeah, 135 miles. David Goggins had never run a marathon, nor had he ever run even a 100-mile race, and yet he still like was able to enter it, which is insane. So he's a crazy person. But you think about like 135 miles, that is definitely relying primarily on your oxidative metabolism. You have run out of glucose by that point. So your body is switching over to fat as a fuel source instead, which is a little bit slower, but very good for low intensity, long duration work. And it is essentially unlimited. I mean, think about like how many pounds of fat we have stored on our body. 1% of your body is carbohydrates, but imagine like, if your body fat percentage is 20%, 20% of your body weight is fat. So that's essentially an unlimited energy source, with so very many calories tapped into it. Yeah, so other things that we need to consider when we're talking about like energy production and energy burn rather, when you're talking about this, we got to think about like the fact of like, well, how much energy does certain types of exercise how much energy do certain types of exercise burn, right? Like how much energy are we consuming? And so like things that we know about this, we know that like lying face up is going to burn less calories than standing up. Which is why, like, okay, if your priority is to burn calories with your clients, well, then you should be prioritizing exercises that have your clients in a standing position, right? Make them do a standing cable chest press instead of a bench press. Now, if their goal is to gain like chest strength, the bench press is pretty great. So it definitely has its purposes there. But we know that like standing burns more calories than sitting. We know standing on one leg burns more calories than standing on two legs, right? And because your body prefers that oxidative metabolism, it likes that long duration stuff for low intensity, right? You're going to be primarily burning fat during these workouts, right? But on the flip side of that, the nice thing about strenuous exercise, which is going to rely not on fat as a fuel source, primarily at least, is when your body burns lots of calories, you experience this post-exercise elevated consumption of calories, right? So excess post-exercise oxygen consumption is an elevated oxygen consumption that takes place after strenuous exercise. So basically, you exercise so intensely, your body will then work to recover over the next, and sometimes this takes up to 72 hours. This can last a really long time, although most of that is pretty limited after, even after 24 hours, it takes a really big dip, but it can last a while, and basically what this is our EPOC here, excess post-exercise oxygen consumption, and this burns lots of calories after you leave the gym. So during intermittent work, so like, we talk about like interval training, right? Glycolysis will provide you the energy to do the high intensity, maximum effort stuff. So glycolysis gives you the energy during your sprints, but then you're recovering afterwards in your oxidative metabolism. So your oxidative metabolism's recovering afterwards. One of my favorite ways to do this that is just incredibly simple is just get on a treadmill, do a 20-second sprint, recover for 40 seconds, repeat, 10, maybe 15 rounds at the most. One of my favorite like treadmill workouts actually that I've never been able to fully complete because I'm not tough enough. But if you ever look up, there's a freaking, if you guys can get through this, it is just an absolutely brutal treadmill workout. But what is it? What is it? What's that guy's name? No. Treadmill sprint workout soccer professional. What's that guy's name? I think, there it is. John Terry, the John Terry treadmill workout. There it is. See, it's in my freaking history. So the John Terry workout, John Terry is this famous soccer player, and he has this like cardio routine that he uses to get him in shape. And what it is, go ahead and skip here, is where you put the treadmill on 18 kilometers per hour, which is 11.2 miles per hour. So you put the treadmill to an 11.2, and you set the incline to, is it 10? 12. So you set the incline to 12, and you put the treadmill on 11.2, and you get it up to speed. So you can see he's actually like kicking the belt to kind of speed the process up. And you do a 20-second sprint, and then you recover for 40 seconds. So he gets on there and he's sprinting 20 seconds. And you'll notice when he gets to the end of the 20 seconds, what he's going to do, he's just going to grab the sides of the treadmill and, plant his feet and stand off to the sides. So wait for him to get to the 20. And there he goes. And he sits and he waits and he recovers for 40 seconds. And he's going to repeat that 5 times. And that's the workout. I've never been able to complete this workout. I cannot freaking do 15 rounds. I have almost gotten to 10 rounds, but nearly every time I've ever tried this, I've had to go like cautiously stand near a trash can where I'm like, I'm gonna throw up. Like, this is gonna happen. It hasn't happened yet, but like it is brutal. And if anybody ever completes it, and I'll give an instant freaking A in the class. that's
I'll do
it. Right? It's brutal, man. It's brutal. But it's great. It's just an absolutely like stellar workout. And so what that does is he's recovering in his oxidative metabolism. He's standing around like, recovering, right? That's very much oxidative. You're not doing any work, right? So because you're not doing any work, your oxidative system is recovering for you, which is great because what does your oxidative system primarily rely on as a fuel source? Fat, right? Now, during the work, glycolysis is providing you the energy. So you produce a lot of lactic acid, you produce a lot of all these materials that are going to be used to be converted into ATP afterwards. So let me tell you, as brutal as this workout is, once the nausea goes away, I feel great. Like all that, lactic acid gets converted into ATP. You leave feeling like $1,000,000 and you are hot all day. And so it creates a massive amount of EPOC, right? That excess post-exercise oxygen consumption. So that can last, sometimes up to 72 hours. This is one of the reasons why I love trail running so much. trail running, which, it's nature's interval training, as long as you try to run at a consistent pace and, recover while you're on your flats and sprint while you're going up your hills, you're going to be in a great place to kind of deal with all that high intensity stuff. And you're going to be burning a lot of fat as a fuel source. So how do we actually like measure this? If we had like a lab to do this, right? How do we measure, how much carbon dioxide we're burning versus how much oxygen? Well, that's where it comes down to what is called your respiratory quotient, or your RQ. This is the amount of CO2 that's exhaled versus the amount of oxygen that's inhaled. So if I bring in 100 units of oxygen and I exhale 70 units of CO2, that's 100 in, 70 out, then I'd be at an RQ of about 70%, right? I'd be at an RQ of 0.7, which means I'd be 100% in the fat burning zone, by the way. That is how much you burn. That's how much you are at by about default, right? So you need a metabolic analyzer to be able to do this, which obviously we don't have access to in a regular gym setting, unless you're working in a lab or something. But an RQ of 1.0 means that 100% of your fuel is being supplied by carbohydrates. And if you're at an RQ of 0.7, that means 70% of your fuel is coming from carbohydrates, right? I'm sorry, 70% of your, an RQ of 0.7 means 100% of your fuel is coming from fat, right? So we're always in a blend, guys, between 0.7 and 1.0. That's where we sit at an RQ. Right now, you're probably at like 0.71 or 0.72. You're sitting down listening to a lecture on Zoom. That's not exactly high intensity. Meanwhile, both of you guys are like at the gym doing burpees. Like, yeah, totally, we're listening. So an RQ of 0.7 is your lowest intensity. That is you asleep, right? So 70% of the oxygen you inhale gets used to do stuff, and 30% of it doesn't. You end up exhaling 30% of the oxygen, which is why CPR works, by the way, when you're doing rescue breaths. If it was 100% CO2, you wouldn't be helping that person out at all, right? None of that, they wouldn't be getting any oxygen. So, but if you are doing like a full on sprint and you're like, breathing like crazy, you're at an RQ of 1.0 or 100% maximum intensity. So that means that all of your fuel is coming from carbohydrates. So an RQ of 1.0, 100% of your fuel is coming from carbohydrates. Your body is working at its highest intensity because you are consuming all of the oxygen that you're bringing in. If it's at 0.7, fat is your 100% fuel source. So your body is working at its lowest intensity. You are only consuming 70% of the oxygen that you are bringing in. So normal life is anywhere from 0.7 to 1.0. So now if we think about like what the fat burning zone is, respiratory quotient, fat burning zone. If you look at your RQ, you can see here, if I'm at like 40 to 50% of my VO2 max, so the volume of oxygen consumed, I'm not consuming very much, right? And that's my maximum oxygen consumption. I know, like, sometimes I look this up and people are like, what do you mean 40%? You just said we consume 70%. Good catch. 40% of your maximum that you can consume. That's where we're coming down to like how many, milliliters of, I'm talking about like how much oxygen you can, consume. So, some people can just bring in more air than others. So if your target heart rate is, between 111 to 137, so this is somebody pretty low, right? Then if we look at how many calories they're burning per minute, this person's burning 5.7 calories per minute. They are very much in the fat burning zone here, as it would be listed on a treadmill, which would mean if we're going to be a little bit, let's get some bigger numbers here. They're burning about 23.7 grams of fat per hour and about 27.6 grams of carbs per hour. So we can see that's, that's not a very, that's a pretty good ratio of more fat, right? And, some carbs here. But you see our calories from fat are 3.9. Our calories from carbs are 1.8. If you're wondering why Remember, the grams of carbs per hour is higher. That's because there's 9 calories in a gram of fat, 4 calories in a gram. That's why the number here is higher, even though the calories here is lower. So this person burned 5.7 calories per minute, which is 1.8 carbs, 3.9 fats. That's a lot of fat in terms of percentage. So what percentage is that overall, right? You know what? Let's modify this. I'm gonna copy this over to Paint so I can write on it. So we look at the fat burning zone, right? We look at the fat burning zone here. 3.9 divided by 5.7. So that's about 68% fat. So that's 68%. And here, that's 1.8 divided by 5.7, which is, yeah, 32%. So that's 32%. Okay, so now, there we go, right? That's a 60-30 split. So yeah, very much the fat burning zone, right? We'll round this down and just call it a 70-30 split, right? That's great in terms of percentages, right? But now let's say they're working super, super hard, right? They're working like really, 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 really hard now. Let's go to like 80 to 90% of their VO2 max. So that's going to be, you know, probably somewhere around like, you know, just the beginnings of zone 3. So now they're burning 12.4 calories per minute versus their initial 5.7 calories per minute. So that's going to be 5.1 divided by 12.4. Now they're only burning 40% of their calories from fat. Was it 41% of their calories from fat? So now they're out of the fat burning zone. But then we look at 7.3 divided by 12.4. That's 59%. And they're burning 59% of their calories from carbs here, right? So now we're going to see that means that they are burning, but they're burning 12.4 calories per minute. So before they were burning 5.7 calories, now they're burning 12.4, right? So that means that the fat calories are much higher here, even though they're at a lower percentage. And this is why the fat burning zone doesn't work the way people think it does. We got to be able to explain this to our clients because they're going to say, I heard working at a low intensity burns more fat than working at a high intensity. And what we need to explain to them is it burns a higher percentage of calories from fat. But because you are burning so many less calories, you end up burning less fat calories overall because you're just not burning as much, if that makes sense. And then you can see like how that breaks down to like the grams per hour as well. So that is where we look at this. And here's the RQ chart. That's actually, this is the one from your NASM textbook right here. So here at an RQ of 0.7, the percentage of calories from fat is basically 100. If your RQ is 1.0, your percentage of calories from carbs is 100. So you are constantly in a blend between those two. And right here, where it is 50% carbs, 49% fat, this is around the fat burning zone. So an RQ of 0.85, I think 0.84 actually is the magic number that is the perfect fat burning zone. But we don't really care about having the perfect fat burning zone because if you're in the perfect fat burning zone, you're not burning very many calories per hour. So it kind of sucks. Now, we tie this in a much more controllable way that's easier for our clients to understand by giving them zones 1, 2, and 3. So instead, we are going to rely on our target heart rate zones. So 65 to 75% of your heart rate max is that traditional fat burning zone that we talk about. But remember, that does not burn very many calories. 76 to 85% is sort of in the middle. 86 to 95% is primarily the carb burning zone, but it burns a massive amount of energy. So this is why we like interval training so much. get into zone 3, recover in zone 1. So you get a big boost of calories because of EPOC, right? Remember the excess post-exercise consumption that takes place after intense exercise. You do the big hard sprint for maybe 20 to 30 seconds, and then you recover for basically double that, or maybe 3 times that much time. If you need 3 times as much time, you can do it that way. But we basically recover for that much time in the fat burning zone. And so we get the calorie burn from the hard work, and we get the fat burning from the recovery. Does that make sense, guys? All right.
Yes, sir.
All right. Well, that is about, I mean, that's what I got for you tonight. So summarizing everything up, bioenergetics, study of how we look at metabolism through, it's how we convert, pizza into, hang cleans. Study of how energy is transformed, right? We've got our metabolism, which is all the chemical reactions. We're going to use proteins, fats, and carbs in order to be able to do that. We are trying to produce ATP, which is the version of energy inside of our body that allows us to do all of our work. We get ATP through the ATP Pc system for about 5 to 10 seconds. We get it through glycolysis for about 20 to 50 seconds, depending on who you ask. We get the oxidative metabolism forever, essentially unlimited. And so we can look at like where we are also burning that energy from, what about the ingredients in that pizza, the proteins, the fats, and the carbs, right? Well, the carbs are going to get burned up from that pizza if you're doing some sprints. And the fats that are found in that pizza, of which there would be many, because pizza is very greasy, we're going to burn that while we are recovering between our sprints, or if you're doing long duration cardio. And that's that, guys. I know it's a little bit of a brief one again today, but hopefully, that kind of summarized up metabolism. This is the last time we're going to talk about metabolism for quite some time. We're going into exercise psychology on Friday, which is fun. I love that class. We're going to talk about like habits. We're going to talk about like some really fun stuff. I've got some really cool extra credit assignments for people who need them in that class, which will be really fun. Then we'll get into our youth program design class, and that'll be the end of this mod. And then the next 2 mods are much less based around physiology and much more based around kinesiology. So we're going to be looking at movement rather than energy production. So we're going to look at like joints and muscles and connective tissue and stuff. So that'll be really, really fun. But you guys made it through another 12-day class. We've got our in-person meeting and our final tomorrow. Hopefully this rain stops. I swear to God, if I have to cancel again because they're going to take away my Oregonian card. It's supposed to be sunny tomorrow, so I don't think we'll have a problem. Questions, comments, concerns? You guys got anything for me today?
All good, all good. I still need to get in the homers and the midterms and for this mod.
Oh, okay. Knock them out.
Yeah, well, I actually printed them out and I did them because I just got back home today. I was working down in Sacramento.
Oh, cool.
Yeah.
What? That's awesome.
That's all right.
You're always how have you been so punctual when you are out of town?
I just listened to you, like you know how you said some people do how do you call it, like if it was a podcast kind of
Yeah, like podcast style.
I just listen to it. Yeah,
love that. I remember when quarantine first broke out, and remember when grocery lines were like, you had to wait for line for like an hour and a half. I had so many students, and they'd have their like camera phones on, so they'd just be sitting there. There'd be like a Ralph's like right behind them and just be in line for like an hour. And I was like, yeah, it's a weird world that we're in right now.
yeah. But it helps that you do the post the YouTube's up because I'm able to follow watch it, more than once, so it's all good.
Yeah, that's the idea, If you ever go to the channel, by the way, you'll find all the old classes, maybe hear like a different version of stuff.
Yeah.
All right, guys. Well, I'll go ahead and kill the recording. Dalen, you feeling good? I heard you say you were good, but give you a chance.
Yeah, it's at 9, Brad. We meeting at 9 again?
Yep, 9 and 6. 9 and 6.
Okay.
All right. I'll see you guys tomorrow.
All right. Have a good one, Brad.
You too.